Hey everyone, and welcome to Ground School. As your flight instructor today, I'm here to help you transform all that dense meteorological data into vital, actionable knowledge that's going to keep you safe up in the skies. Think of this explainer as your comprehensive learning guide to the weather phenomena that govern every single flight we take. We're going to break down these complex principles of meteorology and make them highly intuitive, so you'll know exactly what's happening outside your cockpit window.
Here's our flight plan for today. We'll start with Section 1, the birth of a cloud, followed by decoding cloud altitudes, aviation fog types, the anatomy of a thunderstorm, and finally, thunderstorm classification and avoidance.
All right, Section 1, the birth of a cloud. Let's look at how the sky actually builds our weather. To build a cloud, Mother Nature is essentially following a recipe, and she needs 3 specific ingredients to trigger this exact sequence. First, we have to have water vapor in the air. Second, we need a mechanism to cool that air down so it reaches its saturation point, what we call the dew point. And third, we need something for that moisture to actually latch onto, allowing all that invisible vapor to finally transform into visible moisture through condensation or sublimation. Now, a great way to picture those condensation nuclei is to think of them as microscopic magnets floating around up there in the sky. It could be small particles of salt from the ocean, dust from the plains, or even smoke from a wildfire acting as tiny cloud seeds. Without these particles, the moisture simply wouldn't have anything to grab onto to form the droplets or ice crystals that ultimately make up the clouds we fly through. Moving right along to Section 2, decoding cloud altitudes. Let's start categorizing these formations.
Let's map out our sky by looking at cloud height, shape, and behavior. Down at the bottom, extending from the surface up to about 6,500 feet, we've got our low clouds like stratus and stratocumulus. These are filled primarily with water and, importantly for us, potentially hazardous supercooled water droplets that can cause rapid icing. Moving up from 6,500 to 20,000 feet are the middle or alto clouds, altostratus and altocumulus. Up here, you might encounter some light turbulence and moderate icing on a cross-country flight. Above 20,000 feet sit the high clouds like cirrus. These are made entirely of ice crystals in very stable air, so they pose virtually no turbulence or icing hazards. And finally, cutting right through all these layers on the right, we have clouds with extensive vertical development.
Here is the crucial takeaway for you as a pilot. Clouds with extensive vertical development are extremely hazardous for flight operations. Why? Because they extend from that low level all the way up into the high altitudes, meaning they contain every single kind of water formation imaginable. Whether you're looking at a building cumulus, a towering cumulus, or a full-blown cumulonimbus thunderstorm, these formations bring a truly terrifying menu of hazards. We're talking lightning, hail, tornadoes, wildly gusty winds, severe wind shear, and destructive turbulence.
All right, Section 3, aviation fog types. Let's bring things back down to the surface, because technically, fog is just a low cloud that begins within 50 feet of the ground when the air cools to its dew point. First up is advection fog. This happens when a layer of warm, moist air physically moves over a much colder surface. What's absolutely vital for you to remember here is that advection fog requires wind to form, specifically a breeze up to about 15 knots. But pay attention to this. If the wind speeds up beyond 15 knots, it's actually going to physically lift that fog right off the ground, turning it into a low stratus cloud. You'll very often see this exact mechanism driven by a coastal sea breeze. Picture warm, moist ocean air blowing laterally right over a cold coastal landmass. The land cools the bottom layer of that moving air down to its dew point, and just like that, a thick blanket of fog rolls in over the coast. Next, we have radiation fog. Now, unlike advection fog, radiation fog actually thrives when there is little to no wind. It typically happens on clear, calm nights when the ground rapidly radiates its daytime heat out into space. As the surface cools, it drops the temperature of the stagnant air immediately above it, right down to the dew point. The good news for us aviators is that as the sun rises and temperatures start to increase again, this fog will naturally lift and burn off. Now, if this forms in a very thin layer, we call it ground fog. It is incredibly shallow, we're talking less than 20 feet thick above the surface. This can be tricky because from above, you might see the runway perfectly clearly, but as you descend through it on short final, your forward visibility can suddenly drop to 0. Our third major player is upslope fog. If you're planning to navigate mountainous areas, expect to encounter this one. It absolutely requires both wind and a continuous physical slope to exist. Notice exactly what's happening here.
The moist, stable air is physically being forced upward by the rising terrain. As that wind pushes the air higher up the mountain, it cools adiabatically until it hits its condensation temperature, which completely obscures the slope in a thick fog. To wrap up our fog discussion, you've got to be vigilant about 3 other very specific, very dangerous variations. First is steam fog, sometimes called sea smoke. This happens when cold, dry air blows over warm water. The water evaporates and rises, literally looking like steam, creating severe low-level turbulence and deadly icing conditions. Then there's ice fog. This occurs in extreme cold. We're talking around -25 degrees Fahrenheit or -31 Celsius, where water vapor bypasses the liquid stage and changes directly into suspended ice crystals. Finally, we have precipitation-induced fog. This occurs when warm rain falls through cooler air, evaporating as it falls and saturating the air to the point where thick fog forms.
Let's move on to Section 4, Anatomy of a Thunderstorm. We're getting into aviation's most dangerous weather now.
Listen, a thunderstorm doesn't just spontaneously generate by accident. It requires a highly precise recipe. The ingredients are simple but powerful. Number 1, unstable air. Number 2, a lifting action to initiate the vertical motion. And number 3, high moisture content. If you spot these 3 conditions in your pre-flight weather briefing, a thunderstorm isn't just a possibility, it is practically guaranteed.
A thunderstorm's life cycle goes through 3 distinct stages. It all begins with the cumulus stage, which is characterized by massive lifting action. We're talking intense updrafts, pushing air up to 3,000 feet per minute. Inside the cloud, water drops and ice crystals are growing rapidly as they rise and fall within that updraft. But here's the catch. There is absolutely no precipitation yet. This deceptive building phase usually lasts for about 15 minutes. Right around that 15-minute mark, we hit the mature stage. And this is the most violent, critical phase of the storm's life. It officially begins the very moment precipitation starts falling from the cloud base. The water drops have simply grown too massive to be supported by the updrafts anymore. Now, the storm turns into a vicious, chaotic mix. You've got updrafts racing upward at a staggering 6,000 feet per minute, right next to violent downdrafts smashing into the surface at 2,500 feet per minute. When that downrushing air physically hits the ground, it explodes outward, causing a sharp drop in temperature, a rapid spike in atmospheric pressure, and incredibly dangerous, gusty surface winds. Eventually, the storm exhausts its energy and enters the dissipating stage. The updrafts weaken, and those massive downdrafts of 6,000 feet per minute completely take over the cell. As that upward vertical lifting gets choked off, the storm begins to die out, spreading out at the higher altitudes to form that classic distinctive anvil shape at the very top. Which brings us to our final section, Section 5, Thunderstorm Classification and Avoidance. Let's talk about how to classify the threat and keep your distance. We divide these storms into 2 main categories. First are air mass thunderstorms. These are typically caused by localized convective heating and unstable air. They are usually single-cell events that burn out in less than an hour. However, be extremely careful because they can be treacherously embedded inside other cloud layers, hiding completely from visual sight. On the flip side, we have severe thunderstorms, often called steady-state thunderstorms. These are driven by major weather patterns like passing fronts or converging winds. Because the front keeps pushing the downdraft away from the storm center, the mature stage just keeps going. This category includes supercells, multi-cell clusters, and massive squall lines that can stretch for 50 to 200 statute miles. They can relentlessly punish an area for hours, throwing out wind gusts over 50 knots, massive 3/4-inch hail, and even tornadoes.
Because of the extreme, localized violence associated with these severe storms, there are some strict avoidance rules you need to burn into your memory right now as absolute survival tools. Number 1, you must maintain a distance of at least 20 miles from any intense radar echo. Why so far? Because clear air hail and violent wind shear can literally be thrown miles outside the visible edge of the cloud. Number 2, never, ever try to shoot a gap between 2 storms unless they are separated by a minimum of 40 miles. If they are any closer than that, the converging downdrafts between the cells can produce turbulence strong enough to rip an aircraft apart.
So, we've covered the birth of clouds, the creeping dangers of fog, and the violent, terrifying life cycle of thunderstorms. You now possess the meteorological tools you need to decode the sky. You know what that invisible moisture is doing, and you know exactly how to classify the hazards. But remember this, the ultimate test of a pilot isn't just navigating through bad weather. It's having the situational awareness to look at these clues, respect the immense forces of nature, and know exactly when it's time to keep the aircraft safely tied down on the ramp. The sky is full of clues, but will you have the discipline to say no to a flight? because knowing when to stay grounded is what truly makes a master aviator.